Newsome from Wake Forest University, who talked to us about quantum dynamics in black holes in cosmological environments. I have a quick bio that I want to read. So he did his undergraduate at Appalachian State University in North Carolina. So he double majored in physics and mathematics, and did research in observational astrophysics. He has 2 master's degrees, the relevant one from Virginia Commonwealth University in theoretical physics with research in classical relativity theory, and his PhD in physics from Wake Forest University, where he was a recipient of the Physics Excellent Fellowship and Richter Scholarship. He continues to conduct research in theoretical physics in collaboration with his former PhD advisor, Paul Anderson from Wake Forest University. His current research focuses on analytical and numerical approaches to quantum field theory in extreme environments, including curved spacetime and strong field quantum electrodynamics. He's done research in areas of observational astrophysics, general relativity, and Raman spectroscopy. Let's thank you again.
Okay, well, hello everyone. Thank you very much for the invitation. I'm excited to talk to you about some of my work. Thank you for that very comprehensive introduction. Today I'm going to talk to you a little bit about part of what I did for my PhD, looking at quantum dynamics of black hole and cosmological environments. So let's just jump into it. So the main question I want to cover in this talk is, how do black hole and cosmological horizons modify quantum field correlations and vacuum fluctuations, which is just a fancy way of saying, how does curved space modify the quantum vacuum? A lot of the analysis that I'm going to present can be found in the paper I published last year, PhysRevD, so if you're interested, there's the identifier for it, check it out. I'm going to start with a brief sort of observational perspective to kind of get us grounded with some modern observations, and then we'll jump to some of the details of quantum effects in black hole spacetimes. That sort of sits at like the interface of the work that Albert Einstein obviously did with general relativity, and later when Stephen Hawking brought into the fold quantum effects and discovered things like black hole radiation and black hole evaporation and things like that. I'll then switch a little bit to bring into the fold some cosmological ingredients, and then we'll summarize with some broader considerations and some takeaways. So that's the outline here. Okay, so modern astrophysical observations provide some pretty strong evidence that black holes and the expansion of the observable universe are real. Here I give a couple examples on the black hole side. We can see from the UCLA Galactic Center Group, a bunch of stars orbiting the supermassive black hole in the center of our Milky Way galaxy, which was later photographed by the Event Horizon Telescope in 2022, which is quite an impressive feat. Also, we have from the LIGO collaboration data from stellar mass black hole in spirals, which you can see here. So this has put black holes on a really firm modern astrophysical footing. On the cosmological side, here I sort of give an example of a plot, which is plotting basically something like a brightness-based measure of distance as a function of, think of it as like as a function of cosmic expansion. And this is plotting a bunch of different surveys of type 1a supernova data. And you can see these all fall pretty well on this linear trend. And all that means is this is evidence that the universe is in fact expanding at large scales. And it was, I think, the 2011 Nobel Prize in Physics that was awarded for a group determining that this expansion is in fact accelerating, which we now attribute to this mysterious thing called dark energy. But the point is, from black holes to the large-scale cosmos, general relativity explains a lot of these observations. So let me say a few words about general relativity before we move on. So general relativity, Einstein's theory, there gravity is not really a force in the traditional sense, but rather a manifestation of space-time curvature. It's characterized by the Einstein field equations here. And the only thing I want to say about that is the left-hand side is characterized with the geometric curvature of the space-time through the fundamental object, which is the metric tensor, and derivatives of the metric tensor, how it changes. On the right-hand side, we have the stress energy tensor, which is acting like an energy momentum source, which is sourcing the space-time curvature. And because of this source, space-time can respond in a dynamical way. It can curve, it can morph, it can do all sorts of weird things depending on the source term. And because of that, particles of light that are moving through, traversing this space-time, will follow certain natural paths we call geodesics, which is just a fancy word to say the straightest possible path in a curved space-time. Okay? So the interesting thing here is that there's examples where extreme curvature, okay, extremely strong gravitational fields do this space-time curvature can produce horizons that limit causal contact between different regions of the space-time. So this will be an important point when we jump to the quantum side of things. So there's a special class of solutions to the Einstein equation. They're called the vacuum solutions, where you set the stress energy tensor equal to 0. And this describes empty space-time, where matter and energy content are absent, but nevertheless you can have some interesting curvature effects. One of the simplest examples of this is what's called the Schawrzchild solution, found in, I think, 1916. It just describes a space-time exterior to a spherically symmetric mass distribution. It's pretty good at modeling stars, planetary orbits, black holes with horizons. Here you can solve what's called the geodesic equation. Here I've done that numerically. You can see as a test particle goes around in such a geometry, we have an elliptical orbit with an anomalous precession. This was one of the first successes of general relativity. It was able to verify, because we saw with the Mercury, the orbit of Mercury, we knew this precession, this anomalous precession for the elliptical orbit was a thing, and general relativity was able to verify this, which is one of the first successes. Another relevant space-time solution is what's called de Sitter space. This is a solution which incorporates a positive cosmological constant into the Einstein field equations. And it represents an exponentially expanding space-time. It's relevant for early universe models, like inflationary models, as well as the late-time accelerated expansion, which is asymptotically approaching a de Sitter-like space-time model, like I said before, which is always attributed to dark energy, whatever that is. And here's an animation where we have basically like a blue observer sitting in the middle. We have a red, what's called a cosmological horizon here. It's a cosmological horizon because as the space expands, the green observer here will be carried away from our blue observer, and you reach a point where it goes beyond this special boundary. And this boundary is defined by, if I'm this green observer and I try to send a signal back, the space-time is expanding so rapidly that signal will never reach it. So that special distance is what defines the cosmological horizon there. And so you add these two together and you get the aptly named Schawrzchild de Sitter solution, which is just a combination of both. So we have a black hole horizon sitting in the middle, which is surrounded by a cosmological horizon, outside of which you get the expanding space-time, but the region between the two is what's called the static patch, because it's essentially a competition between the gravitational pull of the black hole versus the expansion of the de Sitter part of the space-time. So if you're in the static patch, there's no like expanding space because the black hole is compensating for it, but once you go outside of that cosmological horizon, you're going to be then causally disconnected from the static patch region. And by the way, if none of this makes sense and you want to just like jump in with a question, please feel free. That's no problem. Okay, so that's the gravity, just a quick recap of the gravity side of things. Now let's jump into some of the quantum side of things. So, So quantum mechanics is the modern theory that describes matter and radiation at microscopic scales. I'd love to include this picture here. This is from the 5th Solvay conference in 1927. This is like one of my favorite pictures because in this group of like 29 people, there's something like 17 future Nobel Prize winners that sort of set the stage for modern quantum mechanics. But since then, there's been a lot of work in high energy experimentation, such as like the CERN with the Large Hadron Collider, where essentially the structure of space-time is found almost every time when you collide these subatomic particles together. And the results of these collisions are remarkably well described by what's called the standard model of particle physics. Here, that's sort of tabulated right there. So this sort of classifies all known elementary particles into different categories, such as matter particles, like quarks and leptons. Hopefully you can see the color coding there. We also have interaction mediators, like the photon or gluon for the strong force. things like the Higgs boson for mass generation. There's still some unanswered questions about this standard model, like, obviously how does the graviton fit into it? Why are there 3 generations of particles, things like that. As far as I know, these are still open questions, but by and large, this is the modern, very successful modern account of the particles that we know of so far. So let me just say a few words about quantum theory. I don't want to get too much into the guts of the theory, but it's useful to say a few things about it. So the quantum mechanics that you learn as like a undergraduate in your first semester of quantum mechanics, that's a non-relativistic version, a particle-based version of quantum theory. And it turns out that that is insufficient for describing relativistic processes in general, in the most general sense. So things like particle anti-particle creation annihilation processes, complicated decay processes like different numbers of particles of different species that are coming into the mix. Your sort of non-relativistic quantum framework can't really account for that in a consistent way. So the modern framework is that of quantum field theory. And in a quantum field theory, you go from what's called a first quantized picture to a second quantized picture, where instead of a wave function that's describing probability amplitudes associated with like particle observables like position, momentum, spin, things like that, you now switch to probability amplitudes associated with field configurations. And this switch in viewpoint where the field is now the fundamental object instead of the particle has been very successful in describing and accounting for a lot of relativistic processes. So like I said, particles are now excitations, I have that in quotes, of underlying quantum fields, where the quantum field, again, is the fundamental object. And so fields being fields, they then obey field equations. There's a number of different field equations you can talk about. The simplest one that's relevant for this talk is called the Klein-Gordon field. It describes a spin-zero scalar field. A scalar field is just a special kind of field that just attaches a value to every point in space. It has no other degrees of freedom. Here's just the equation of motion for that. This box guy is just a special type of covariant differential operator. That's all. But you can have other sorts of fields like the Dirac field, which is spin 1/2 fermionic field, Maxwell field like spin 1 electromagnetic field, and other types of gauge fields. And I say all that to say is that the current standard model that I just talked about on the previous slide is essentially just a collection of all these different field theories and their interactions. And so I thought it might be useful as one more thing to talk about one type of quantum theory, which are the quantum theory of free fields. In a free field theory, you're not considering any interactions. And the way this sort of works, just to kind of get you comfortable with the formalism, is you take a field phi, or scalar field phi, and you what's called Fourier expand it in terms of a basis set of mode functions, right? This u and u star. Now think of this as like, if this is weird, think of it like when you take a vector in the plane, right? You decompose a vector into basis vectors, right? Like x hat, y hat. Well, this is kind of like an analogous version for fields. You take it and you expand it in terms of basis elements, which are called basis mode functions, that are parameterized with respect to this k thing, which is just like your momentum of the field mode, okay? Now you have these other things, these A and A dagger guys, which upon quantization will be your creation and annihilation operators. And so your field becomes an operator which acts on the quantum state, and you can create and annihilate quanta of fields, okay? So that's how that works. Here I kind of give sort of a classical example of that, of what that looks like. Here on the left we have just sort of a phi of x, a field amplitude is a function of some spatial position x. We have the corresponding Fourier amplitude as a function of its momentum or k value. And so when I let this run, you can see the field configuration in space is going to do all sorts of weird things. But fundamentally what's happening is you have these Fourier modes that are acting like little independent harmonic oscillators, right? Each one of these for a given k is treated like an independent harmonic oscillator. And it's when you sum up over all of them that you get some sort of field configuration in space, all right? That's the basic idea. And when you quantize it, what you're quantizing are these Fourier modes, okay? You're saying, I'm going to treat each one as an independent oscillator. And so what you can do, okay, is, I'm skipping a bunch of details here, but the thing that is really interesting about this for a free field theory is you can take your basis set of states, it's not a Hilbert space anymore, it's what's called a Fock space, which is just sort of a bigger Hilbert space, you can think, that takes into account all sorts of different states of different particle number. And you can diagonalize that state space with respect to the particle number. So I can have a vacuum state, I can have a 1 particle state, a 2 particle state, and the thing that gets me from one to the other are these creation and annihilation operators that your field is built out of. Okay, so the field is acting like the thing that helps transport you through the state space that respects special relativistic considerations like Lorentz invariance and causality and all that jazz. So one last point on this. The vacuum state here is kind of an interesting thing because although the expectation value of your field in the vacuum state is 0, and that just comes from how the creation annihilation operators behave, the fluctuations of the field, this phi squared guy, when you take the expectation values, in general not 0. And this shouldn't be too weird of a concept because if you just think back to like your normal quantum harmonic oscillator, right, the average position of a particle in a harmonic oscillator potential is at the middle of the well, but it can fluctuate, right? When any given measurement of it will probably not be that average value. So this is just the quantum field version of that, okay? So this will come back to play later on. So talk a little bit about gravity with relativity. We talked a little bit about quantum field theory. So now, how do these two guys play together? How do these two fields come together? So a fully, like a bona fide theory of quantum gravity is going to give you something like a probability amplitude associated with your matter field configuration as well as your geometric configuration. Okay? Current status of a quantum gravity theory, as far as I know, I'm not an expert on all things quantum gravity, but as far as I know, there's no complete experimentally verified theory of quantum gravity. There's all sorts of candidate theories. I'm sure you know string theory, maybe you've heard of loop quantum gravity. These are some of the more popular ones. Where here you have fundamental strings that make up all the fundamental particles we see in the standard model. You have loop quantum gravity, which sort of discretizes space-time at the fundamental level. But these are still just candidate theories, even though they've been around for a long time. As far as I know, there's no evidence for any of them. So where I live with my work is a slightly more conservative approach, which is called semi-classical gravity, in which one considers quantized matter fields on a classical space-time background manifold. Okay, so we're not quantizing the space-time metric or anything, we're just quantizing matter fields and see how they behave on a classical space-time structure. And the way this looks is you take your Einstein equation that we started with, and now you just replace the stress-energy tensor with an expectation value, because your stress-energy tensor is now going to be built out of these quantum field operators. So that, to leading order, the mean for sort of approximation would just be the expectation value. And you're going to have higher order quantum corrections, which can include things like fluctuation terms, back reaction effects, things like that. But at leading order, we're just going to replace our stress tensor with its expectation value. And this has been a very successful sort of procedure. I mean, Hawking's result about horizon radiation associated with black holes, that was a semi-classical result. Particle reduction in expanding spacetimes, like inflationary cosmology, that's a semi-classical calculation. As well as in electrodynamics, you can have certain semi-classical effects, such as like the Schwinger effect, which I'm not going to go into, but you can ask me about later if you want. That's another type of semi-classical effect. So this paradigm of semi-classical physics has been really fruitful. And yeah.
Have any of these physical semi-classical predictions been observed or by experiment?
So I'll come back to that, but as far as the ones I'm aware of, no, they haven't been. So like Hawking radiation has not been experimentally verified, although there are some interesting lines of work that replicate using Bose-Einstein condensate black hole, like acoustic black holes, where I don't know if they've seen Hawking radiation analog with those yet, but I know that's one like research direction that may give some insight.
Yeah, so that's exactly right. They claim, but then people are like, maybe not. So but that is one. So they're analog systems, though. So they're not gravitational systems, or like the Bose-Einstein things, like you said. Right.
And I'll say a little bit more with the Hawking radiation why it's so hard to actually on this slide. That's a perfect segue. Thank you for that question. So that was just sort of the in broad strokes where I'm coming from with semi-classical gravity. So let's say a little bit about Hawking radiation. So Hawking's original calculation, he did it for a black hole that formed from dynamical collapse. And he was able to show on theoretical grounds that black holes emit thermal radiation as seen by a distant observer. You can attach a temperature to that radiation that's proportional to the surface gravity of the black hole. And here I did just as a sample calculation for a 1 solar mass black hole, the temperature of the Hawking radiation would be something like 10 to the minus 8 Kelvin. And you may be aware that the current cosmic microwave background radiation is something like 3 Kelvin. So in terms of experimental verification, there's no way you're going to see that until like a Google years into the future when the universe is cooled down to a point where this actually becomes non-negligible. Okay, so but the origin of the Hawking radiation really comes from a mismatch between the quantum vacuum state that I described previously. It comes from a mismatch between the quantum vacuum state before and after the horizon forms, okay? So you can think, I have a set of basis, think about my field expansion. I can have a set of basis modes that define the quantum vacuum for the initial configuration of the star. Then we have gravitational collapse, and the vacuum state and the modes associated with it after the horizon forms are not in general the same, okay? And the horizon is going to induce this really weird mixing of your quantum field mode functions that makes it look like particles are being emitted from the black hole when you observe it from really far away. So here I have sort of a little cartoon that might help frame this a little bit better. So the 2D slice here is just a 2D physical space, and the vertical axis here you can think of as just like your quantum field amplitude. So the blue background is your little bubbling quantum field vacuum. As your star collapses and it forms a horizon, that horizon is just going to disrupt the vacuum in a very weird way, because it's going to cut off some of those basis mode functions that you started with. And what that looks like from far away is a thermal spectrum here. Here's sort of the average particle number you would detect from very far away. It follows a thermal spectrum indicative of like a black body radiator, and it carries with it that temperature T. So that's sort of a cartoon version of the Hawking effect, how the black hole horizon just disrupts your vacuum, and it makes it look like from far away you're getting radiation out of that. Okay, so dynamical collapse models theoretically are a huge pain in the butt to deal with, because there's all sorts of insane modeling and computational work you have to do to actually get something interesting. So stationary spacetimes are much simpler to deal with as theoretical laboratories for investigating quantum effects. So one such model is the Schawrzchild spacetime that I mentioned previously. Here I'll just say a few words about this Penrose, it's called a Penrose diagram, which is essentially just a global map of the causal structure of that spacetime. The relevant areas are region 1 as well as region 2. So region 1 is the region exterior to the black hole, like you and I are living in region 1 right now, compared to like our supermassive black hole in our Milky Way. This is what's called, this line right here is the past black hole horizon, which is just an artifact of the eternal space-time model. This is a black hole that exists eternally, so it's not formed from collapse. So you have a past black hole horizon. This surface is called future null infinity. You have a future black hole horizon here, as well as future null infinity. Null infinity is just like the surface that all your things that are moving at the speed of light will accumulate on in the far future. And you have region 2, which is the black hole interior. So you can think of you in a spaceship or whatever. You would start down here in the infinite past. You would move along a world line through time, and your space, you're getting closer to the black hole horizon. You'll cross it, and you can see once you cross it, your light cone structure like forces you to stay within the black hole, and you'll eventually terminate at the singularity, which is this jacket line. So this understanding of Penrose diagram will be useful for what I have to say later. So, as I said, this type of stationary spacetime model is really useful for understanding quantum dynamics. You can study them very precisely. And let's see, how am I doing with time? Oh, okay, I'm okay. So, let me stop and say maybe a few things about vacuum states before we move on, because this will, I think, help the discussion. So, in a flat space, quantum vacuum that I discussed is in a sense globally defined, in a very broad sense. What that means is there's a special class of a of observers that will agree on what the vacuum state is. And those are your inertial observers, okay, in the flight. But you will always agree, all inertial observers will agree on what the quantum vacuum state is. However, when you go to curved space-time, or any really time-dependent background, but in this case a curved space-time, that notion of a global vacuum state goes away. And what that means is you can have multiple different vacuum states. The vacuum state is no longer unique, which means you can have different observers that will locally have different notions of the vacuum. Okay, so in one observer's frame, they may see no particles in their vacuum state, but in a different observer's frame, they may detect particles using the same vacuum state. So weird things happen. So there's two relevant vacuum states that I'm going to talk about, the Bulbar state and the understate, so let me quickly review those right now. The Bulbar state was a particular type of vacuum state that was designed to replicate the Minkowski vacuum very far away from the black hole. The only thing to really say about it is those mode functions that you expand your field in terms of have a very special form that you impose on the past black hole horizon as well as past null infinity. So the only thing that I really want you to care about with this is this 1 over root omega that's here. That'll be important later on. But the YLMs here are just your spherical harmonics. These are positive frequency with respect to a static time coordinate. If that doesn't make any sense, don't worry about it. It's not super important. But just know that we have a set of mode functions that we're going to force to look a certain way on the past horizon in this little theoretical laboratory. Now these are complete in the sense that they cover all the space. Like you can think of this as like a Cauchy diet or a Cauchy surface. You can think of it as complete in the sense that they cover all that. You can then expand your quantum field in terms of the complete basis of these modes with associated creation and annihilation operators. And what's useful about this is your stress tensor, the thing that's sitting on the right-hand side of your Einstein equation, goes to 0 asymptotically far away. So that's what I mean when I say it replicates the Minkowski vacuum really far away. However, it's not appropriate. What we really care about is describing Hawking radiation, right? So this is not an appropriate vacuum state for describing that because there's no outgoing particle flux really far away. So we're going to switch to another state called the understate. Okay, this is a year after the Bulbar state drop. So this is going to this was a state that was designed to replicate the thermal flux of Hawking radiation really far away. So this guy Bill Andrews said, well, what can I do to get the right thermal spectrum? And he said, well, if I switch my black hole Bulbar mode here, which is on this horizon, if I replace that with what's called a crustal mode, that's positive frequency with respect to a different coordinate. Again, don't worry about what that means, just recognize that there's a different coordinate sitting here. Okay, when I do that, that's going to be defined across the entire black hole, past black hole horizon, and that in fact will give me the correct spectrum of Hawking radiation. Okay, again, this is complete, so I can take my field, expand it in terms of a complete set of these mode functions. And the only thing I'll say about this is your stress tensor is infinite at the future black hole horizon here, as well as future null infinity, which again gives you the Hawking thermal spectrum. It diverges on the past horizon, goes to infinity here. That's okay, because past horizon is not astrophysically realistic. Okay, realistic black holes don't have a past horizon; they form from some finite time in the past. So it's not such a big deal that this blows up in the past horizon. So these are the two states I want to really focus on for the remainder of this talk, which is about Schwarzschild de Sitter space-time. So again, Schwarzschild de Sitter space-time has two horizons, a black hole horizon and a cosmological horizon, okay, outside of which you have de Sitter-like expansion. So the geometry for this horizon in spherical coordinates looks this way. This is your line element. This f of r function is just your metric function that goes like 1 minus 2m over r minus a squared r squared. The only thing to take away from this is it involves the black hole mass as well as this h squared function, which is related to the cosmological, the positive cosmological constant. So just think of h as like essentially the cosmological constant that controls the expansion rate. So we have a Penrose diagram for this as well. The only difference here is future null infinity, which was sitting right here before the Schwarzschild case, has now been replaced by the cosmological horizon, this outer ring, and future null infinity has been pushed up here. So region 3 would be this like cosmological far field outside. Region 1 is the green region here. So that's where we're going to focus the quantum analysis on. Okay. So the understate has a natural generalization to the space-time. Okay. So what you do is you take the crustal mode we had, and then you just replace the Bulwar mode that was on past null infinity before with another crustal mode that's positive frequency with respect to a different crustal coordinate. So we can set up these special crustal modes to be defined on the union of the past black hole and cosmological horizons in the following way. What's interesting now is both of these horizons carry with them a Hawking radiation. They carry with them a separate temperature. So we have a black hole temperature associated with this Hawking radiation, as well as now a cosmological temperature associated with the radiation of the cosmological horizon. And these, in fact, in general, will not be the same. So in the static patch, in this region, in general, you're going to have sort of a non-equilibrium thermodynamic kind of situation going on. But nevertheless, these are complete in the mathematical sense, so I can take my scalar field, expand it in terms of a complete set of these modes. And then given the specific form of these modes, if the general form that these take off the horizon, so these have a very specific form on the past horizon, but if you look at general points in the sort of bulk region, when you plug these modes into the original mode equation, you're going to get a very, very ugly, gross, nonlinear partial differential equation you're going to have to solve numerically, okay? Which takes a huge amount of computational time and isn't really that physically enlightening. And the reason is because these crustal modes are not separable in these particular crustal coordinates that they're defined with respect to. So what are we going to do? So we're going to use our old friend, the Bulwar state, which is why I brought it up before, to help us with this. So the Bulwar state has a generalization to STS as well. Okay, and again, pick a certain form of the modes on the past horizon. These are complete. What does that mean? That means if they're complete, I can take any function, including my crustal modes, for my understate, and I can expand them in terms of complete sets of these Bulwar modes, okay, because they're complete. That should be fine. Now, the thing to take away, though, is in this expansion, these hideous-looking coefficients, these alpha and betas with all these subscripts, okay, those are what are called Bogolubov coefficients, because this is called a Bogolubov expansion, which is a weird name. But the interesting thing is that the thermal properties associated with the understate, right, from the Hawking radiation are built into these alphas and betas, because these alphas and betas are really characterizing how the two sets of modes mix together. Think of it like a very complicated dot product, where you take A vector dot B, you're seeing how much of A is on B. Well, here we're seeing how much one set of modes is projected onto the other set of modes, okay? And that's where your thermal character is going to emerge in this theory from these alphas and betas. They have a specific closed form. It's super ugly. It's not super enlightening, so I'm not going to bore you with that. But so now we have to talk about, okay, what the heck's going on with the Bulwar modes? Because we're using them as a way to simplify solving the mode equation for the scalar field and for general points in the bulk region here. So what's going to happen is the general form of these Bulwar modes, the black hole and cosmological modes, are going to look exactly like they looked before, except now your radial mode function is not going to be some plane wave. It's going to be some generic function of R. Why? Because when you plug these into your original mode equation, you're going to be left with this, what looks like a 1D Schrodinger-like scattering equation, okay? Which has an omega squared term. You think of that as like the energy, even though there's, it's tricky in gravity, but just think of this as like the energy, and we have an effective potential term that shows up here. This effective potential term didn't show up at the horizons. It goes to 0 at the horizons, but when you want to consider points in the general static patch, it shows up, and it has this particular ugly form here. The only thing to say about it is it depends on the metric function, so it depends on the space-time geometry, as well as your angular momentum quantum number. So this is sort of like a centrifugal barrier term. So what's going to happen is when you start a mode on the past horizons, when they evolve forward, some of them will transmit all the way through on either side, but a lot of it's going to get scattered away as it's moving through. And that scattering is characterized by the physics of this effective potential. There's two main points I want to make about this. That is the effective potential for the spherically symmetric, or L equals 0 case, in which case it has a large positive barrier close to the black hole horizon and then goes negative as it approaches the cosmological horizon. Whereas for higher L modes, here I give L equals 1, but it's true for any L greater than 0 mode, all you have is a large positive barrier that does not go negative. This is going to have huge implications for what goes on with the quantum field dynamics later on. But just recognize it's negative for the spherically symmetric case, it's not negative for any other case. Okay? So let's talk about the infrared behavior, which is to say when the frequency associated with this Bulwar mode, remember this Bulwar mode is this oscillating mode in space, so it's going to be a sum of a bunch of different frequencies. And the one we care about are the infrared modes. Why? Because of how the effective potential behaves there. So here's our scattering equation. So for the L equals 0 case, like I said, it goes the effective potential goes negative for part of the static patch region. What is that going to do? As omega goes to 0, that means this whole other term is going to be positive. What's that going to do? Well, that's going to give you oscillatory solutions at low frequencies. Okay. What that means is there's another 1 over root omega that I pointed out before. So that 1 over root omega times your radial function for L equals 0 is going to be infrared divergent. Okay. Whereas for L greater than 0 case, the effective potential is positive everywhere, and the same thing you get out of that are exponentially suppressed solutions, in which case you're infrared finite. So we're getting this weird infrared divergence that's showing up for our infrared Bulwar modes due to the presence of this effective potential going negative, which is really weird. So I'll say more about that in a minute, but here I'm plotting some numerical data. This is just essentially just plotting the magnitude of the Bulwar mode. The spherically symmetric Bulwar mode is a function of its frequency. You can see here I'm doing this for multiple different radial coordinate choices between the two horizons, which I parameterize in the following way. At high frequencies, the omega squared term dominates, and the modes approach their sort of no scattering form, which is indicated by the sort of colored dashed lines here. But as you get to omega squared being comparable to the effective potential, you see there's a lot of dampening of these modes as you go to lower frequencies. And as we keep going to lower frequencies, you can see they all approach this straight line. This is a log-log scale, so this is indicative of that 1 over square root omega. This is our infrared divergence. So we can see this happening numerically, as well as the arguments I provided here. So now we're sort of at our bedrock. We've solved this Bulwar mode, this radial mode equation. We've constructed our Bulwar modes, but remember we started with Kruskal modes associated with the Unruh state. That's what we really care about. So now we're going to build those back up. So because we have this weird infrared thing going on in our spherically symmetric sector, you can write your Kruskal modes in terms of, here I'm doing it explicitly in terms of the combinations of the Bulwar modes here. There are just a few things I want to point out. This is, I don't want you to like understand every single bit of this. There's just the radial solution that I was just talking about is built into these A and B functions. We have this plane wave term here and here, which involves our static time coordinate that's being shifted by some phase that's proportional to the surface gravities, as well as the Kruskal frequency omega. Keep in mind this omega here is different than the omega you're integrating over. This is the Kruskal omega, whereas this is the omega prime is your Bulwar mode omega. There's two different frequencies. And lastly, you have this weird shift in this 1 over omega prime where I'm shifting it into the complex plane. Why am I doing that? That's a mathematical trick because we have, again, the infrared divergence. So this is going to blow up at omega equals 0. So I'm shifting it into the complex plane. And the main physical takeaway I want you to take or get from this is at late times, remember the Unruh state is the state that replicates Hawking radiation at late times. So at late times when T gets really large, the large frequency part of this is going to give you a lot of like deconstructive interference. Right? These are going to oscillate super rapidly and you're not going to get much contribution to the interval. However, as you go later in time, you get smaller and smaller frequencies that are going to contribute coherently to this. So this is kind of like a temporal filtering effect where the later in time you go, the smaller and smaller frequency contributions you're going to get from the Bulwar modes. And for arbitrarily late times, the reason this doesn't just completely destructively interfere, again, comes from that infrared divergence you're going to get at omega equals 0. I say all that to say, skipping a bunch of details, you can do the complex integration, you'll get a residue from the pole, and what this does is it makes your Kruskal modes, defining your Unruh state, go to constants at late times. Okay, that's the important point I want you to take away from this. These Kruskal modes go to constant at late times. This constant depends on the global features of the space-time. It depends on the size of the black hole and cosmological horizon. We also have this 1/√omega showing up. And we can see this numerically. Here I'm plotting numerical results from the amplitude of the real part of the crustal mode as a function of time. You can see I'm doing this for a number of different frequencies, and they all sort of approach this constant at late times. The amount of time it takes for them to approach this constant is inversely proportional to the frequency, so smaller frequencies hit that constant later compared to larger frequencies. Similar results hold for the cosmological crustal modes. But then the fact that these approach constants at late times is completely coming from the weird infrared divergent behavior of your crustal modes. This doesn't happen for the L greater than 0 modes. All these will just go to 0 at late times. So again, the spherically symmetric sector is really driving some weird dynamics. Okay? And so now, that's all well and good. We've got our quantum field and the understate sort of worked out. We've got solutions to it, but we don't really care about that. What we really care about are physical observables, right? So again, going back to our semi-classical Einstein equation where we've got the quantum stress energy tensor sourcing the right-hand side, this quantum stress energy tensor is going to depend intimately on this special type of function I haven't talked about yet. This is called the Hadamard two-point function. This capital G, this is not an exponent, this is just a label, capital G1 of xx prime. So it's a two-point function. It depends on two space-time points. The local vacuum fluctuations, which I talked about before, also depend on this in the coincident point limit of the Hadamard function as well. So a lot of the observable behavior is coming from this Hadamard function. So now that I've got my quantum field mode solved for the understate, let's actually look and see what this Hadamard function is doing. Okay? In general, the Hadamard function is given by the vacuum state expectation value of the anti-commutator of your field at different points. Don't worry about why that is. That's just the way it works out. And for the next slide, what I'm going to do is I'm going to isolate my analysis to looking at different. Remember, this two-point function depends on two different space-time points. So I'm going to look at two different radial points, but let the times become equal. So I'm going to look at a coincident time hypersurface and two different radial points in the static batch. So what happens? Well, so the Hadamard function takes a very specific form for the understate. It basically just goes as this integral over your products of black hole and cosmological crustal modes at different space-time points, x and x prime. And the total function is a combination of all the angular momentum components of that. But again, it's the spherically symmetric L equals 0 sector that's really being weird. Okay, we're getting this weird infrared divergence in our Bohr modes. We're getting these weird late time constants that are approached by our crustal modes. So what effect does this have on the Hadamard function? So when you plug it all in and work it all out, you get this result here. What does this say? This is the L equals 0 contribution to my Hadamard function. I have this very weird growth rate. I have a linear growth in time, and then I have some other function, f of r prime, that's not super important. The thing I want you to take away from this is this, in fact, represents a type of instability with this state. Why? Because the linear growth in time, that's our static time coordinate. Time is the domain of that's minus infinity to infinity. So what this is saying is at arbitrarily late times, I'm getting arbitrarily large correlations in my field, which literally become infinitely large, in the limit that I go into the far future. And the rate at which that's growing linearly is given by this guy here. Again, it depends on the black hole and cosmological surface gravities as well as the radial values themselves. So like I said, this represents a type of infrared instability associated with this state. Again, the understate is the most natural state for a black hole spacetime. It gives you the Hawking result. So this is a big deal. This is one of the main results of that paper I published. So we can see this happening numerically. Plotting the Hadamard function as a function of time for two different radial coordinate values. This is a very complicated plot, obviously. So we have linear growth. The red points here are the numerical results. The black dashed line is the late time analytic approximation. That comes from the late time crustal modes, those constants I showed you previously. So we have really good agreement between the numerics and the analytics. So this is a real bona fide instability. So let me just say a couple comments how am I doing? So I'm almost done. We say a couple comments about the growth rate itself. Again, it depends on the global features of the space-time. It also depends on the surface gravity. So remember, the surface gravity is related to a temperature. So in a sense, this growth rate is driven by I'm not going to say the thermodynamics, but driven by the thermal properties of the horizons themselves. So this is a total thermal phenomenon due to the Hawking radiation from the horizons. You can plot this growth rate as a function of the black hole radius. The blue points here are just numerically determined values. The red curve is the analytic form of the rate. In the limit that the black hole radius goes to 0 and you approach pure de Sitter, this result agrees precisely with the results of these guys in Allen and Falachi who worked this out for a scalar field in pure de Sitter space. The other extreme, when the horizons come together, when your black hole horizon comes together with your cosmological horizon, the growth rate goes completely to 0 because you don't really have a static patch anymore, so there's nothing to like correlate in the middle of them, which is a good check. It should do that. And there's also sort of a maximum value that the growth rate is somewhere in the middle of the two. I don't remember exactly what it might be like 1 over, I don't, it's in the paper. I don't remember exactly, it's some random number. Those are just some interesting properties of that. That's the Hadamard functions. Now let's go back to local vacuum fluctuations, phi squared. I'm running out of time here, so let me just quickly run through this. From the Hadamard function, you can compute phi squared. Local fluctuations are formally UV divergent, which just means they blow up for arbitrarily large frequencies. You can renormalize that, but that's a complicated procedure. It can be done, but it's not as useful because all we really care about is the time dependence. So another shortcut for that to characterize the understate fluctuations is to subtract from it the associated phi squared for the Bulwer state. This is time independent, which means this quantity the time dependence of this total quantity will only reveal the time dependence of the understate phi squared. And the UV divergences associated with both of these will be the same. UV divergences, you just have to take my word, they are state independent. So when you subtract them, the UV divergences will cancel out. You'll get something finite. And when you plot this as a function of time, again, you see the linear growth, the linear instability that's occurring. Both the analytic and the numerics apply together, great agreement. And so to get a little bit of like intuition about what the heck this is really telling you, again, if you take a classical field, fix it at the endpoints and plot it as a function of space and let it run, it's almost like you'll have these sort of higher fluctuations, but it's almost as if like the long wavelength contribution to this is causing the amplitude of this to sort of just grow stochastically over some period of time, which is really, really weird, right? So it's almost like the infrared part of my quantum field is doing some sort of stochastic drift almost. I mean, it's very, very strange. So I'm almost done. I'm almost out of time, so let me just quickly say a few things about some questions that I thought might be interesting to answer. So is this fluctuation instability that's been discovered, is it physically observable? This is where we're kind of getting into a little bit of speculation territory. My current opinion is yes, I think in principle it can be observed, but only as like a statistical accumulation sort of effect, not like as an instantaneous signal. What I mean by that is I could very easily imagine in a sort of perfect SPS environment having a little particle detector that I would couple to my field, and then I would take measurements of the particle content due to the Hawking radiation. And what this instability might tell me is that as time goes on, the variance of my measurements will increase. So it's almost like this is like a horizon-induced quantum noise type of phenomenon. Okay, if that makes sense. So I think in principle it's observable, but in practice it's probably just as hard to measure this as it would be to measure Hawking radiation in the first place, because in the observable universe you have lots of other things going around. You've got cosmic microwave background radiation, you've got gravitational waves, all sorts of things that might muck up this infrared coherence effect that's going on. Okay, so does this actually translate to the stress energy tensor, right? The stress energy tensor depends on derivatives of the Hadamard function, which we know is linearly unstable in time. And so Disappointingly, no, I don't think it will, because these derivatives will kill off the linear instability. So this probably won't translate to anything like a real space-time instability at the level of the stress tensor that would induce some sort of kind of weird curvature effects. But I think more so, it's just, the thing that would just be thought of as like more of like just an infrared accumulation of the infrared part of your quantum field. Lastly, is this instability a consequence of eternal black hole space-time models? So the answer to that is sort of yes, sort of no, actually, because there have been other models that look at what are called null shell collapse. That's those are black holes that are formed from the collapse of like literally just a shell of energy that's coming together at the speed of light to form the black hole. There you have a well-defined, here's a Penrose diagram for that. The blue line is the null shell collapse. There you have a well-defined end state instead of like imposing Pruskal-like boundary conditions. And even in that case, you still get late time linear growth to leading order. So what this is telling you is this is not an effect that's coming from the details of the collapse itself, which is, it kind of in a sense makes perfect sense, because Hawking's result was didn't depend on the details of the collapse either. So this is probably just a verification of that idea. And also, black holes are thought to evaporate, so they don't exist forever, right? At some finite time in the far future, you will have a black hole, and then you won't have a black hole. So this linear growth in time is really only an instability when you consider infinitely far into the future. But what you're probably more likely going to have is this weird quantum noise that's continuously accumulating and stacking up over time, and it will get capped at a certain point that's correlated with the black hole evaporation time. So like I said, it's more of just like a quantum noise effect that's introduced due to the presence of the horizons, rather than some sort of like legitimate space-time curvature instability. So this is my last slide. Again, let me just, some of the takeaways. We looked in 4D STS, where you had a black hole horizon and a cosmological horizon, and how do those modify the field correlations and vacuum fluctuations of a scalar field. We looked at the understate, which incorporates Hawking radiation from the horizons. We looked at the massive scalar field, the spherically symmetric sector. We have late time unbounded linear growth in our field correlations as well as our local variance. This linear growth is generated by like a coherent stacking of your large wavelength infrared Bohr modes that at the level of the two-point function generate this linear growth in time. And the last interesting, I just recently sort of thought about this a number of weeks ago. This linear growth in time is oddly reminiscent of the linear growth you get for Brownian motion. I don't know if you guys are super familiar with Brownian motion, but the basic idea is that I've got a little particle in a medium, and it sort of has this random walk due to the random energy that it encounters in the medium. There, the variance of the position of the particle grows linearly in time, right? So in this sense, maybe this is sort of like a horizon-induced quantum field version of Brownian motion for the infrared part of your quantum field, because that also grows in time. And maybe the diffusivity constant that's present in Brownian motion might be related, in this case, to all these global features of the space-time. So, and therefore, the last thing I'll say is that might allow you to admit sort of a stochastic semi-classical description for that sector of the quantum field, which has all sorts of implications about, like, okay, the probability density associated with the field configurations. There's all sorts of interesting takeaways you can get from that, but that's the final thought I'll leave you with. So I hope some of this has made sense. I'm happy to take any questions. So thank you.
I like to talk a lot. So so if you're an observer between the Schawrzchild horizon and the cosmological horizon, I saw you wrote down two temperatures, one for, and basically they both depend on the surface gravity. So at what temperature does that observer between the horizons, what do they see, right? Do they see the left one, the right one, or some combination of the two?
I mean, it would be some combination of the two. You have like a sort of non-equilibrium thermodynamic environment. But because the temperature is proportional to the surface gravity, the black hole one would be much larger than the cosmological one. although, as an interesting point, although that's the case, the black hole surface gravity is going to be more than the cosmological one, so that temperature is going to be larger. If you look at,
But you did consider the case where the two horizons meet, right? So, I mean, which was just artificial, but,
I didn't consider it numerically,
okay.
but, because there is no static patch to solve for the dynamics within when they meet.
But so to get to that point, you have to take a limit of the two horizons
Right,
running into each other.
right.
So, you know, so you could look at it, so is it as like an artificial question, you could say, okay, well, suppose the two horizons grow close to each other, you're in between, so what is the temperature then?
Like for like arbitrarily small.
Yeah,
So as the black hole, so there's an interesting relationship. So the size of the black hole horizon sort of controls everything. So as the black hole horizon gets bigger, the cosmological horizon is going to necessarily get smaller because they're related to each other. So as the black hole horizon gets larger, its surface gravity is going to go down. So its temperature is going to go down. But as the cosmological horizon shrinks, I would imagine its surface gravity would be larger. So I'm not exactly sure, I have to like plot it out and see, but I'm not exactly sure how those two effects would compensate. Maybe you get exactly the same temperature, non-equilibrium temperature throughout the middle, but I suspect probably not. But I don't know exactly what it would be. I haven't looked into that, like that specific limit. But you reminded me of something I forgot to say, which I'll just say really quick. Even though the black hole, the surface gravity is larger, this combination, r squared times the surface gravity, is in fact smaller for the black hole than it is the cosmological part of this. So what this is telling you is that the cosmological horizon is actually, in terms of this growth rate, is giving you a lot more contribution to the growth rate than the black hole, even though the surface gravity by itself is small. Because RC squared is going to be much, much larger than RB squared, especially on like a realistic cosmological scale. So, just an interesting thing I forgot to mention. Yeah.
So if you look at your last slide,
The very last one?
the very last one, right, the instability you got from the Hadamard function, what happens to that if I kill the de Sitter part?
So if you kill the de Sitter part, remember this entire effect fundamentally is originating from that negative part of the effective potential. So if you kill the de Sitter part, that will totally go away and your effective potential will be positive for the whole static patch. So you're not going to get this infrared accumulation. You won't have like the infrared divergences.
But if I just kill it over here, it seems that the black hole piece stays in there, so that it's still linear in time.
That's an interesting question. Well, then the boundary conditions of your space-time will totally change then if you kill off the cosmological horizon, because then you're not assigning a crustal mode onto the past cosmological horizon. You're going to assign, I guess, a Boole mode or something else to give you the understate. That's an interesting question. I'm not sure. I'm not sure.
No, the reason I'm asking is because you know that de Sitter is unstable.
De Sitter is, yeah.
Right, okay, so classically it's stable, quantum mechanically it's unstable. So does this instability have anything to do with that?
You mean the instability that was like found by like Allen and Falaci? Is that what you're referring to?
Just purely quantum effects in de Sitter, right? That tells you that de Sitter is unstable. Anti-de Sitter is unstable, classical and quantum.
Yeah.
This guy is unstable only if you have quantum effects. So is this instability a reflection of that?
I think this instability is related to the instability that you see in de Sitter space, certainly.
Okay.
But I'd have to think more about that to really give you a serious answer. But like I said, and I showed in that plot, like the limit of the black hole goes away and you just keep pure de Sitter. What we have exactly matches what the Hadamard instability that was already discovered back in 1985, which is one of the big checks. But in the opposite end, if you take away de Sitter space completely and you're just left with Schawrzchild, I know it may seem like you should still have an instability, but I want to say, I know in at least in 1+1 gravity, for pure Schwarzschild, this instability doesn't show up at all.
Uh-huh.
So something, I think it has to do with how you define the boundary condition on the horizon. So, I mean, it may seem like it is here, but that's just a guess. I don't know for sure.
Okay.
I'd have to look into that to say
Alright.
more. But, yeah.
So what current research is being done on Hawking radiation? Like, is there any experimental group that's trying to verify that?
Experimental group?
Yeah.
Oh, I haven't bothered to look. I mean, not that I know of. I mean, other than the Bose-Einstein condensate analog black holes, I'm not aware of anyone who's like trying to astrophysically measure. Well, I mean, I guess in principle you could measure it if you go really close to a black hole with a particle detector, because there the temperature goes up, right, as you hover above the horizon closer and closer. The temperature you would measure will blow up. So you could in principle measure it if you're willing to get arbitrarily close to a black hole.
So, or you could hope that they're like small mass black holes, because if you looked at the formula, right, the temperature was inversely proportional to the mass.
Yeah.
So for a solar mass black hole, when our sun doesn't end as a black hole, well, the temperature is like painfully small. But if you had like a moon size black hole, I think the temperature is like 3 Kelvin or something. And if it's smaller, then it's higher,
Yeah.
right? And so, and I think that Hawking originally said, so they asked him the same thing. It's like, his temperature is pretty small for astrophysical black holes. He's like, well, maybe there's primordial black holes that formed from collapsing fluctuations in the early universe. And these things you might see as like gamma ray bursts. So it's something like that. But that's kind of a hope, right? More than a...
Yeah. That was one potential explanation for the gamma ray burst we see for like the, what is it, like the quasars and the galaxies on the sort of the edge of the universe that we were picking
Yeah, so
up.
he's like, oh, maybe that's it.
Yeah. I mean, one sort of extension of this work that I'm doing is looking at the far field region of SDS. Maybe I'll just say a couple comments about that. Where's that? Yes. So in this region, this is asymptotically de Sitter, right? But you're still going to pick up some remnant of black, some modification of the modes that make it out to this region due to the presence of the black hole. So one thing I'm looking at right now is looking at, we're starting to look at how modifications to the inflationary power spectrum, or how they would be modified with black hole effects, to see if that might, if you could see any sort of, any markers of that on the cosmic microwave background, because, you know, in inflationary cosmology, to make a long story short, you know, the primordial fluctuations that you had mentioned that sort of come back into the horizon once inflation stops, you know, you might have black holes that form from that, or you might have black holes that form prior to an inflationary epoch, you know, prior to the hot Big Bang or whatever we all theorized to occur. So one thing I'm working on is looking at modifications to the power spectrum due to the presence of the black holes to see if there's any chance of seeing that. That might give evidence for some sort of primordial black hole. But that's still in the works. That's not an easy calculation.
I have a question with the analogy with the diffusion.
Yeah.
Is that because you are basically confined, like the gravitation basically takes this quantum and basically overlapping over each other, just like, you know, particle diffuses and has basically infinite number of collisions, and that's where the correlation
So,
stimulates, or...
That may be true. That wasn't quite what I had in mind when I first made that connection. I mean, the connection could be total BS. I mean, it's just pure speculation, but it just seems like there's got to be some connection there. So, for example, what I had more had in mind is with this sort of picture here, it's the long wavelength contribution to this wave that's sort of drifting stochastically in the same way that like a little Brownian motion particle would.
I was
maybe
thinking the
trading
exact
walks.
same
That's-
thing, honestly.
That's the connection. So maybe this is some sort of stochastic drift of that long wavelength contribution to that quantum field mode across the static patch. I wouldn't know what to say other than that. I haven't looked into it enough.
There are no more questions, that's something that I'll speak
Have you?
You can come down and ask him.
I was going to say, did you try solving with arbitrary function f of r instead of plugging in Schwarzschild and consider?
No, definitely not.
Too hard.
Because the f of r, I mean, the horizon structure in some sense is fixed by the f of r function. So that might, I mean, maybe you could do it, but that would be too generic of a.
Yeah,
you would-
sometimes it's doable because of the high symmetry, but yeah.
Yeah, but I mean, the reason it works here is because you can apply certain boundary conditions of the modes to give you the Hawking radiation, but if you just did it for some generic f of r, like, I mean, I don't even know how you would set up the initial value problem. Like,
Okay.
I mean, you'd have to pick something, whether it's de Sitter or Schawrzchild or something else. Okay.
Thank the speaker again.